And where we left off yesterday was page 3 of your notes. And we ended where we were on finishing up example 5 yesterday. And we came up with the cubic polynomial p of x. Right? We wrote it out, but we did not sketch it yet. Okay? So is anybody who took a stab at sketching it? No? So let's see if we come up with the same thing. Okay? So in example 5, the cubic polynomial p of x that we came up with is equal to minus 1/9 times x minus 1 times x minus 2 squared. Okay? So the x-intercepts in this graph are at x equals 1 and at x equals 2. So we'll graph those. I went one step further. I actually calculated the y-intercept, right? And the y-intercept, right, you put in 0 in for x. That's what y is equal to. So when you put 0 in for x, we have y is equal to minus 1/9, 0 minus 1, 0 minus 2 squared. And when I did that arithmetic, I got y is equal to 4/9. That's the y-intercept. So that helps me come up with a little more accurate graph. Okay. So here's my coordinate plane. We have x-intercepts at x equals 1 and x equals 2. Oh, and we're also in the definition of this function, right? You're given that p of minus 1 is equal to 2, which means the point minus 1, 2 is on the graph. So here's minus 1 on the x-axis. Here's y equals 2. And so here's the point minus 1, 2 on the graph. And I don't think we had discussed the in behavior in the graph of this thing yesterday, right? What's the degree of this polynomial? 3, right? You just add the exponents, right? 1 plus or the multiplicities. 1 plus 2 is equal to 3. So the degree n is equal to 3. And the leading coefficient is minus 1/9. Right? So if we were to expand this, multiply this out, the leading term would be minus 1/9 times x cubed, right? Because remember, the leading term has the form a sub n times x to the n, where n is the degree and a sub n is the leading coefficient. Odd degree, negative leading coefficient. What's going to happen on the left end? Yeah, it's going to go up, right? And on the right end, it's going to go down, right? So from this point here, it's going to go up. And over here on the right end, it's going to go down. Okay. Well, we also calculated the y-intercept is at 4/9. So here's y is equal to 1. So 4/9 is roughly halfway. And so the graph is gonna come down across the y-axis, right there, roughly 4/9, which is roughly halfway between 0 and 1 on the y-axis. And at x equals 1, the multiplicity is 1. So does the graph cross the x-axis at x equals 1, or is it touch and turn? Crosses, right? And what about at 2? Touch turns, because the multiplicity is even, right? So this isn't going to be perfect. We're not trying for perfection here. It's going to go, right, cross at x equals 1, form a turning point, come up, touch the x-axis at x equals 2, touch and turn, and then go down forever on the right end. Okay? Now that's a crude sketch of the graph, right? Using what information we know. We know there's points on the graph, right? We calculated the y-intercept is 4/9, so it's going to cross roughly right there. We know x equals 1 is an x-intercept. It's going to cross at x equals 1. X equals 2 is an x-intercept. It's going to touch and turn. And we know it's going to go up on the left forever and down on the right forever. Okay? And so that's using that information, we can get a rough idea of what the graph looks like. Okay? Yes, ma'am.
Could you explain the negative 1/9 and x to the third again up here?
Over here?
Yeah.
Well, the leading term of an unfactored polynomial, unfactored, okay, is of this form, right? A sub n times x, right? That's from our definition of polynomial function at the top of page 1. Right? So, focus. Okay? Top of page 1, right? Polynomial function degree n. A sub n times x n is the leading term. This is the leading coefficient, and that's the degree of the polynomial. So we deduce that the degree is 3, right, from the multiplicities, and we calculated the leading coefficient to be minus 1/9.
Okay.
Yes, sir. So putting those two pieces of information together, we create the leading term of the unfactored polynomial. Okay? Mm-hmm. All right. Any other questions? All right, so let's take a look at example 6 at the bottom of page 3. And it says, sketch a graph of a polynomial p of x that has a 0 of multiplicity 1 at x equals 1, a 0 of multiplicity 2 at x equals minus 1, a 0 of multiplicity 3 at x equals minus 3, and then satisfies these two conditions. Okay? So let's break this down. So 0 at x equals 1, right? That's an x-intercept, right? 0 is an x-intercept, so the same thing. And it has a multiplicity. Let's do it this way. I'm going to create a little table. Okay? So we have the x-intercept, or 0 as it's called, and the corresponding multiplicity. So the x intercepts at x equals 1, and it has a multiplicity of 1 at x equals 1, okay? Then we have an x-intercept at x equals minus 1, and it has a multiplicity of 2. So the x-intercept, or 0 at x equals 1, the multiplicity is 1, right? That's odd. And then the x-intercept at x equals minus 1, it has a multiplicity of 2, and that's even. And then we have a 0, a multiplicity 3 at x equals minus 3. Well, 3 is odd, okay? So, we know at 1 and minus 3, the graph is going to do what at those x-intercepts? Cross, right? So you're going to cross at x equals 1, and at x equals minus 3, and then at x equals minus 1, the graph's going to touch and churn, right? Because the multiplicity is even. Okay. All right. So let's draw coordinate plane. And we got zeros at minus 1, minus 3, and plus 1. All right. We need one other piece of information, the behavior. And that's given to us right here. It says P of x goes to minus infinity as x goes to plus infinity, right? So remember, on the x-axis, plus infinity is way out here on the right end, and minus infinity is way out here on the left end, right? And with the y-axis, minus infinity is down here at the bottom, and plus infinity is up here at the top, right? And it all has to do because the positive numbers on the x-axis are on the right side, the negative numbers on the left side. With the y-axis, the negative numbers are below the origin, and positive numbers are above, okay? So it says P of x, saying the graph of the polynomial is going to minus infinity as x goes to plus infinity. Okay? So the further out you go out here on the x-axis to the right, the further down the graph goes. So it's going to go down on the right. Okay? And then the second condition is that P of x goes to minus infinity as x goes to minus infinity. Okay? So that means the further out you go on the left side of the x-axis, the further down the graph goes. Okay? So both ends are going to fall in the graph of this polynomial function. Okay? Well, that helps us how to graph at the x-intercepts, knowing what the end behavior is. Okay? So both, you know, P of x, the graph goes to minus infinity in both these cases, right? As x goes to plus infinity, as x goes to minus infinity. So we could write both ends fall. Okay? All right. So at minus 3, at x equals minus 3, the multiplicity is odd, so we know the graph is going to cross the x-axis. At x equals minus 3. At x equals minus 1, the multiplicity is even, so the graph is going to touch and churn. So we're going to form a turning point And then the graph comes down and it touches and turns at x equals minus 1. Okay. Now we don't know exactly where it crosses the y-axis, right? We don't have enough information, but it's going to cross the y-axis somewhere. And we know at x equals 1, the multiplicity is odd, and so the graph is going to cross at x equals 1. So to the right of minus 1, right, at some point, we've got to form a turning point. And then the graph is going to come down and cross at x equals 1, and then go down forever. So we have graphed the end behavior, successfully graphed the end behavior, and graphed the behavior at each of the x-intercepts. Okay. Now, it's just a crude graph, right? It's not intended to be exact. Okay. So any questions on that? Okay. All right, so you flip over to example 7. Back to our word problems for a moment, right? Section 2.9. An open box is to be made from a rectangular piece of cardboard, 12 feet by 6 feet, cutting squares at side length x feet from each corner and folding up the sides. So what's step number 1? Draw a good picture, right? So let's do that. So we have a piece of cardboard that's 6 feet wide and 12 feet long. And we're going to cut square from each corner that's x by x feet. We don't know exactly what x is, but it's x by x feet. And then once we cut out the corners, we fold up sides to create a box, right? Glue the corners together, right? Create a box with an open top. Find an expression for the volume of the box, v of x, as a function of the side x cut out at each corner. So this is where you got to visualize. So when we cut out these 4 corners, x by x feet, and fold up the sides, this rectangle right here will be what the bottom of the box, or the base of the box is. So this rectangle here represents the base or the bottom of the box. Okay? Now, the length of our piece of cardboard originally was 12 feet. But when we cut out the corners, x feet by x feet, and fold up the sides, the length of this base right here is going to be 12 feet minus 2 times x feet. Because we lose x feet here, we lose x feet here, and so we subtract 2x feet from the total length of 12 feet to get the length of the base. Okay. X plus 12 minus 2x plus x equals 12 feet. So we lose 2x feet when we cut out the corners and fold up the sides. Okay. Well, we got something similar happens with the width. Right, the total width is 6 feet. When we cut out the corners, right, we're going to lose x feet up here and x feet down here when we fold up the sides. And so the width of the base or the bottom is 6 feet minus 2x feet. Okay? So the width of the box is 6 minus 2x, the length is 12 minus 2x, and then the height of the box is going to be x feet, right? Because these sides get folded up to form the sides, right? These flaps, as I call them, get folded up to form the height of the box. So the volume of the box is width times length times height. The width of the box is 6 minus 2x. The length of the box is 12 minus 2x. And the height of the box is x, right? Because that's the size of the squares that we cut out from each corner. And fold up the flaps. The flaps are x feet long. Okay. So that's A, right? It says A, find an expression for the volume of the box as a function of the size x cut out at each corner. Now here's something that you guys have been wanting to do all semester. Use your calculator, okay? Use your calculator to approximate the value of x, which will maximize the volume of the box. So in doing that, I went to one of my favorite websites for graphing, Desmos. So what?
That Symbolab one?
Say that again?
That's like Symbolab or something?
Oh, okay. But this is the website, right, that I've done. And so I typed in the equation here, okay? 6 minus 2x, y is equal to 6 minus 2x times 12 minus 2x times x. The domain for x is 0 to 3, right? The width, the size of the square has to be at least 0, but it can't exceed 3 because you put in 3 in for x here. If the square is 3 inches by 3 inches, you have no width because the width of the piece of cardboard is only 6 feet. So 6 minus 2 times 3 is 0. So the maximum width, so the square has to be less than 3 feet. If it's exactly 3 feet, you end up cutting away the entire width of the piece of cardboard. Okay. So 0 to 3 is the domain for x. And so there's a maximum, right? This is the volume based upon the size of the square that we cut out from the corner. And so you can see the maximum is right here. Well, what's that value of x that maximizes the volume? So it's roughly 1.3. Remember, this is a point in a coordinate plane. So this is x, and this is b of x, the volume. So the size of the square that maximizes the volume is roughly 1.3. Okay. So for b, I put x is equal to 1.3 feet. You don't ever have to go more than first decimal points, okay? And you should be able to verify all this on your own computer, okay, that I'm putting on here. Any questions on that? Yes, ma'am.
On your b of x, the x at the end, where did you say it came from? The last x in the.
Right here?
Yeah, where did you say that one?
Comes from the square. From the square that we cut out of each corner. The corners are x by x.
Okay.
And so when we cut out that corner, we basically have a flap here, and we fold the flap up to form the height of the box.
Okay.
So this is the base. So if you're looking at this box from the left end, okay, it has a height of x, and a width of 6 minus 2x. And if you're looking at this box from the side, it has a height of x and a length 12 minus 2x. Okay? So these, once the corners are cut out, this is why you gotta visualize. Why I think visualization is very important. Because once you cut the corners out, you fold those flat to form the height of the box. Okay. All right. Yes, sir.
So is there any way we could find the answer for B without having to
Do a graph?
Yeah.
It's called calculus.
For the sake of
Yeah.
because this is like use a calculator to find x. I guess we would never have that on exam.
Because this is a third degree polynomial.
Yeah. So you
And we know how to find the maximum quadratics.
Yeah.
So
So I was gonna say
calculus-
you can't find the vertex here because it's a
That's right.
polynomial.
Yeah. Yeah. So, but in calculus, you won't have any problem finding the maximum. Okay, once you learn calculus techniques. Yeah. Okay. That's what I love about calculus, doing cool stuff like this. All right. Any other questions? All right, let's cover the intermediate value theorem. And then you'll have everything you need to complete the homework once I release it, okay? So this is a calculus topic. Suppose that f is continuous on the closed interval from a to b, and that n be any number between f of a and f of b, where f of a and f of b are not equal. Then there exists a number c in the open interval a to b, such that f of c is equal to n. What on earth are they talking about? Okay, so let me draw a picture for you of what they're talking about. And so you might want to draw the picture. Here I drew it right there, above example A. And I'm just going to draw this in the first quadrant. You can draw it anywhere, quite fine, okay? But f is a continuous function on the closed interval from a to b, right? So you know this, or this open, closed interval from a to b. So you know this values of x, right? So here's x equals a. Here's x equals b. Then you know y values and function values, right, are the same, right? Y equals f of x. So the y value at x equals a is f of a. The y value at x equals b is f of b. Now, the way I've drawn this, okay, the way I've drawn this, f of b is greater than f of a, but that doesn't have to be the case. They could be switched, okay? I just got to draw them somewhere, okay? Now, f is a continuous function on this interval, right? So, you can trace out the graph of this function from x equals a to x equals b without taking your pencil off the paper, okay? There are no holes or gaps or jumps or anything like that, okay? Now, n, capital N, is any number between f of a and f of b. So here is, right, here's f of a and f of b, and I'm just picking an arbitrary point between right? Point between f of a and f of b on the y-axis. Yes, ma'am.
Why did you choose that shape?
Oh, I just pulled it out of the air.
Okay, so it can be,
It could be anything as long as it's continuous.
okay.
Okay. It can be anything as long as it's continuous. And it has to be a function. It has to pass the vertical line test, right? Can't be some crazy graph that fails the vertical line test. Okay, it's got to pass the vertical line test in order to be a function. Okay, so I just pulled that out of the air, right? This shape. Okay. Now, so our function is continuous from x equals a to x equals b, and f of a and f of b are not equal, and n is some number between f of a and f of b. What the intermediate value theorem then says, there has to be some number on the x-axis between a and b. I'm going to draw a horizontal line over to my graph, and then a vertical line down from that point. There has to be some number between a and b, we'll call it c, such that the function evaluated at x equals c is equal to n. That's what the intermediate value theorem is saying, okay? If our function is continuous, right, from a to b, then there has to be some number n between f of a and f of b, where for any, let me rephrase that, there has to, for any number between f of a and f of b, there has to be some number between a and b on the x-axis such that f of c is equal to n. Okay? That has to be true just because it's continuous. Okay? The function is continuous. Okay? That's the intermediate value theorem. Follow me? Does it make sense? Right? That if this function is continuous from x equals a to x equals b, and these two y coordinates are not equal, right, at x equals a and x equals b, then for any number between f of a and f of b, there has to be a number between a and b on the x-axis such that f of c is equal to capital N. Okay? That has to be true just because the function is continuous. Okay? All right. So let's look at example 8. It says, show that there is a root of the equation x cubed plus 2x minus 1 is equal to 0 in the interval from 0 to 1. So we're going to prove that using the intermediate value theorem. So we have x cubed plus 2x minus 1 is equal to 0. Okay? So what this is saying, there's a value of x. When it says the interval from 0 to 1, okay, there is a value of x between 0 and 1 such that it makes that value of x makes the left-hand side equal to 0. Okay. What is that value of x? Well, we're not going to find a value of x. We're just going to prove that one exists. Okay. So you can, the left-hand side here is a polynomial, right? Degree 3. So we're going to let f of x equal this polynomial on the left-hand side up here. X cubed plus 2x minus 1. So you know when we set this equal to 0 and solve for x, we're looking for an x-intercept, okay, in the graph of this polynomial function, where it crosses or touches the x-axis. Well, this is a third-degree polynomial, and you know from page 1 of your notes, when we talked about the power function degree n, the graph of the polynomial function is continuous, right? The graphs of all polynomial functions are continuous. So f of x here is a third-degree polynomial, So we can write f of x is continuous on the interval from 0 to 1, right? For values of x from 0 to 1, okay? Values of x from 0 to 1. Well, let's calculate the value of the function at x equals 0 on the left end of the interval. F of 0 is equal to 0 cubed plus 2x minus, f of 0 is equal to 0 cubed plus 2 times 0 minus 1, which is equal to negative 1. So f of 0 is equal to negative 1, which is less than 0, right? What about on the right end of the interval at x equals 1? F of 1 is equal to 1 cubed plus 2 times 1 minus 1, which is equal to 2. And 2 is greater than 0. Okay. So in the graph of this polynomial function, from x equals 0 to x equals 1, okay, at f of 0, this is the y-intercept, right? At x equals 0, so the point 0 minus 1's on the graph. At x equals 0, right, the value function is minus 1, right? That's the y-intercept in the graph of this function from x equals 0 to x equals 1. And we know at x equals 1, the value of the function is 2. So the point 1, 2 is on the graph. So Theo, if this function is continuous from here to here, does the graph of this function have to cross the x-axis somewhere? It does, right? There's no way you can go from here to here without crossing the x-axis if the function is continuous, okay? So, now I don't know exactly how the graph looks. I'm just connecting the two dots, 2 points. And so there's a point here between 0 and 1, we'll call it C, where the value of the function at x equals C is equal to 0. Okay. So by the intermediate value theorem, IVT for short, okay, the graph of f must cross the x-axis. Therefore, and we're just given a proof, right? We're not going to actually find the number C here where it crosses the x-axis. Therefore, there is a real number C in the open interval from 0 to 1 such that f of C is equal to 0. Okay. We're basically saying there is an x-intercept between 0 and 1. Okay. And we're proving it because the function is continuous. it's below the x-axis at x equals 0, and it's above the x-axis at x equals 1. So it's gotta cross the x-axis somewhere between 0 and 1. Alright, any questions on that? Alright guys, have a very good fall break, 4-day weekend. I'll see you next Wednesday.